Okay, so I hope my screen is visible in presentation mode.
Yes, ma'am, it's visible.
Right, right. So, good morning to all of you. This is our class for CED 2 course. If I consider last class, there we have discussed the related to shell and tube heat exchanger. We have started with the accessories involved in this, like how to choose the tube dimensions, and then once I'm having the tube dimensions, then shell diameter and that bundle diameter, how we need to calculate what is clearance and all that we have discussed, and we have continued that with specification related to shell. Okay, like what should be the shell dimension, how what are the standard dimensions, what are the arrangement in shell, there are different E, F, G, like that. So those are basically standard, what we can say, the standard name has been given by TIMA, which is the association which I have discussed in the last class, and then we have discussed how to choose baffle cut and baffle uh, spacing, and tube sheet thickness, how we need to consider that, and then tie rods and all. So all that accessories we have discussed, their standards, values which are available, and how you need to choose the correct one, right? So that we have discussed, and also we have discussed the complete design procedure, as you can see in the present slide also. So the whole procedure we have discussed, and that what we need to do stepwise we have discussed, as you can see over here. And if things are not in a permissible limit, what we can do, and that how we can proceed, bring how we can bring the design to the feasible range, so that we have discussed. Now in today's class I will discuss this design procedure in brief, in detail, discussing each and every step of this. Okay, so let's start with the first one, that is the define duty, use energy balance to compute unspecified flow rates and temperatures, flow rates or temperature. Okay, so as we have discussed, in the last class also, that when we consider design of any shell and tube heat exchanger, uh, or not only shell and tube, but double pipe and all. So we are only given with five parameters, which we can say the specified parameters are five only. Like M1, if you see, M1 is kg per hour, is the process fluid is to be cooled from T1 to T2. So if you see, for process fluid we need three parameters: M1, that is flow rate, and starting, or we can say the supply or target temperature, or initial or final temperature of one fluid. Okay, it will exchange heat with another fluid which is available at M2 kg per hour and at temperature T1, small t1. So M2 would be the flow rate of second fluid, and T1 is the temperature of second fluid. Otherwise you may be given like inlet and outlet temperature of second fluid is T1 and T2. M2 you need to find out. Okay, in that way you can consider the parameters which are given, but only five parameters will be given to you. Okay, and other the whole design you need to consider, you need to perform before proceeding with the design. That is one thing. So once I'm having this, all these five parameters, the first step is define duty. So can I define duty over here? Okay, if you see the if I need to define the duty of a heat exchanger, that is nothing but mcp dt. Okay, so if you see here, for one fluid I am having m, I am having t1 and t2, right? But I don't have cp value, specific heat. Okay, so to calculate duty, or we can say define duty, you need to go for second step, and that is basically collect physical properties. Here only cp we will not calculate, we will calculate other properties as well, because these properties will be used in further calculation like heat transfer coefficient and all. Okay, so you need to find out the or not find out, you need to collect the physical property from the standard approach, or standard graphs, standard tables. So if you see, I will discuss how to find these physical properties. Okay, so the first property we have is the viscosity of the liquid. Okay, and if you see this graph is basically, it has x and y value, capital X and capital Y, and on this left side I am having the temperatures. Okay, in degree Celsius as well as degree Fahrenheit both, and here I am having the viscosity, centipoise. Okay, cp, you aware of this unit, centipoise. So in that way we can have the viscosity of liquid, and this viscosity will depend on the x and y parameters. Okay, so to find this x and y, which is what we can say, which is uh, different for each fluid, not fluid, liquid, which is different for each liquid. If you see here, I'm having liquid, and liquid the names are available over here. I'm having x and y values. Okay, so these values are different. Okay, this table continued here as well. Okay, so to give an example, if let's say I'm having any fluid, you can consider, let's say if I'm having hexane. Okay, if I'm having liquid hexane, which I need to uh, consider as process fluid. Okay, so x is 14.7 and y is 7, right? So come go back to the previous uh, graph, 14.7. If you see, x is 14.7, somewhere like here. 14.7 will be, this is 15, so 14.7 somewhere here, but here I am having this 6 and 7. Okay, so this point will be, I hope you are able to trace the point as I am pointing out. Okay, so this one should be the point, and uh, what I can say over here, uh, so if you see 14.7 and 7, somewhere here I'm having the point, right? And let's say your temperatures are uh, for for processed fluid, or I can say for one fluid, inlet and outlet temperature will be given to you. So you need to find out average temperature, and that average temperature you need to locate over here. Let's say that average temperature is like 50 or 60, let's say 60. Okay, so what you need to do, you need to draw a line like this, start from here, a straight line, sorry, following this point, and then wherever it will cut this line, wherever it will cut this point, this will be your viscosity point. Okay, viscosity value. I'm sorry that straight line I'm not able to draw, but I can, but I think you can understand that you need to match this 60 and this point where we have located the value, and wherever this straight line cut this right scale, that we consider as the viscosity of the liquid. Okay, so in that way you will collect the viscosity, which is one of the physical property. Okay, this is the table, and this graph and table, these are not available in volume 6, these are available in Sarth book, RW Sarth book. So I will provide that these standard tables to you. Okay, so but I hope you understand how to find this viscosity. Okay, similarly this is for gases. Okay, and here
Excuse
I'm
me, ma'am.
having the, sorry.
Are you presenting the slide with tables? And because we
Sorry.
are here, we are just being able to see the flow chart, the first slide.
Yes.
So this, ma'am,
Okay, that it is not visible.
no, ma'am. This actual slide is visible, but I guess the slide you are presenting hasn't changed.
Okay, just 1 minute. This is visible only, right? Like flowchart you are able to see.
Yes, ma'am.
Okay. Uh, and now it is moving to hyperlink. That hyperlink you are not able to see, I guess.
No, ma'am.
Okay, just give me time. Mm, sorry for that, actually. Uh, is it visible now? Yes.
Yes, ma'am. It's visible.
Okay, so let me restart with this. Actually, I have kept things in hyperlink, so it is easier to move here and there from hyperlink. Okay, but no problem, I will restart this. So, as far as physical properties are concerned, if you see here, I'm having this uh, graph where I'm having this x and y values. Okay, and if you see the left side, this is the temperature line in Fahrenheit as well as degree Celsius, and here I'm having the right scale is for viscosity point. Okay, so if I consider this viscosity curve, this is viscosity for the liquid, and for this x and y, if you see here, I'm having the uh, x and y values for different liquids. Okay, if you see, each liquid has different value of x and y depending upon the properties. And this table, if you see at the bottom, it is written continued. So this table continued here as well. Okay, so in that way we can find out x and y. Now I will show you how to collect the value from this graph and from this table. If I consider hexane, for example, okay, here I am having 14.7 and 7, right, x and y values. So go back to the graph. Uh, and if you see here, I'm having 14.7x. So somewhere it will lie here, and 7 on y-axis. So somewhere here. Okay, you can see the value over here. I hope you are able to see the dot which I have put. Fine. So if this is the point which you have located depending upon the fluid, sorry, depending upon the liquid. Here I'm having the temperature line, and this temperature line, how you need to locate the point over here, like you are already aware of inlet and outlet temperature of one fluid. Okay, so you need to start you need to collect the property for that fluid only where you are aware of inlet and outlet temperature, because you need average temperature to see the value. So let's say your average temperature is coming as 60 or 50, whatever. So if it is 60, what you need to do, you need to trace, you need to draw a straight line from this point following this dot, and wherever it will cut this, what we can say, right scale, that value you need to choose as viscosity. Let's say if I am considering over here, okay, following this point, where, sorry, what happened, following this point, I don't know how, some has that discontinuous there, but I hope you understand that how to collect this. So if I draw the straight line, and wherever it will cut this right scale, that value you need to choose as the viscosity. Okay, so that viscosity is in centipoise, you need to convert that into kg per meter second to bring it to the what we can say, unit uniformity. Okay, so I hope in you understand to find out viscosity of the liquid in this way. Okay. Similarly, I am having the viscosity of the gases. Okay, x and y values you can see over here. Okay, x and y value you can see over here, and that you can locate over here. Temperature you can see from here. Draw a straight line from this temperature to that point, wherever it will cut this axis scale, that value we consider as the viscosity of the gases. Procedure is same for all. Okay, just a moment. Right. So in this way you can see the viscosity of liquid and gases, and another important property we have is the specific heat of the liquid. So specific heat of the liquid, if you see here, I'm having this values, and each liquid has separate or different numbers. If you see, okay, each value has different numbers. Similarly, each value each liquid has different number, and the value which will be available over here, it will be what we can say, suitable for this range. Okay, that left scale is showing the temperature as we have discussed in the viscosity, and right scale is showing the specific heat in this calorie per gram degree Celsius. Okay, so if you consider any parameter like if I'm having, let's say, hexane again. Okay, hexane has the number 35, if you can see over here. So you can locate 35 in this. If you see here 36, 35 is this, right? You can see 35. This dot, or this small circle shows the what we can say, it locates the hexane. And if you see this axis, this is the temperature scale. Temperature scale you need to consider for average temperature. Okay, so you need to locate that point in temperature, draw a straight line from this point to 35 circle, and straight line wherever it will cut this scale, this is a specific heat that you need to consider. Okay, so in that way you can consider the specific heat of different liquids, and that you need to find at average temperature. Actually, average temperature is not only for a specific heat. Whatever property you are considering, all those properties should be collected at average temperature. Okay, so from the given 5 parameters, you need to start the calculation of heat duty or other calculation for that fluid for which both the temperatures are known to you. Okay, so what will happen, if both the temperatures are known to you, you can find out average value, you can find out, you can collect all properties for that fluid. Okay, and once I'm having the CP value, you can define the duty, right? So in that way you can collect this. And how to find out that a property for other fluids, that next sorry, for second fluid, that we will discuss. Okay, so in that way you can find out viscosity and specific heat. Here I am having thermal conductivity of the liquid, so you can see hexane. This is not much you need to do, you only need to see the temperature and see the value. Okay, if hexane is there from 86 to at 86, the value is available. At 140 degree Fahrenheit, value is available. So if your temperature is in between these two, you can what we can say, interpolate, or if value is beyond that, you can extrapolate. Actually, value of that C thermal conductivity does not vary much. Okay, so that interpolation and extrapolation that you can do for the fluids, for the liquids. Okay, so this table you can see. Okay, so all these tables and these property charts, these are available in that Sarth book, which I will provide to you. I don't know whether you have that book or not. I will provide that. Okay, so that is about the about the property. Now coming back to this graph. So I hope this flow chart is visible now. Hello.
Yes, ma'am.
Okay, okay. So in that way you can see the physical properties and density. That again, one chart is, one table is there that I will provide you, that I have not shown over here, but I will provide that to you. Okay, this is, that is a simple table. Just you need to see the locate the fluid, sorry, you need to see the liquid, and then you can see the density value from that table only. Okay, so this is for one fluid for which both the temperatures are known to you. Okay, now how you will do further? If you know the specific heat of one fluid, inlet and outlet temperature and mass flow rate, you can define heat duty now. Okay, and next is how to find out the unspecified temperature and or unspecified flow rate by making energy balance simply. Fine, MCP dt of one fluid should be MCP dt of another fluid. So MCP dt of another fluid, when you are considering, you need to collect the CP value for that, or a physical property for other fluids also. Okay, if you are given with one flow, you are given with flow rate and one temperature only, right? So how you will collect the physical property? Because physical property you can calculate only at average temperature, and that will require the temperature, that will require uh, the second temperature of second fluid. I hope you are able to follow me. Okay, so in that case, what you will do, uh, one temperature is already known to you, Okay, one temperature is already known to you. You will assume what we can say. You will assume, let's say, specific heat. Okay, because the first property you require is the specific heat. So you will assume specific heat of that fluid. Okay, irrespective of the temperature, you will you can assume any value. Okay, there is no guideline. Okay, so that specific value, you will specific heat, you will assume, you will make energy balance. mcp dt of one will be mcp dt of another, and from that you will calculate second temperature or unknown temperature of the fluid. I hope you are able to understand. So unknown temperature of another fluid. Now you will have both the temperature, inlet and outlet of another fluid, second fluid. Now you will calculate average temperature of that fluid. On that average temperature, you will see specific heat value from the chart. Okay, that specific heat value should be equal to the assumed value. If it is so, it is fine. Otherwise, you need to take the new specific heat value, make the energy balance, calculate the unknown temperature, then again calculate the average temperature, see the specific heat value from the chart. So this iteration will keep on continuing till you will have two consecutive specific heat values equal, right? I hope you are getting my point. So once I'm having the specific heat value, correct specific heat value, it means the unknown temperature you can fix. Once you fix the unknown temperature, you can have average temperature of second fluid. At that temperature you can collect other properties also directly, like viscosity, thermal conductivity and all. Okay, so in that way you can collect, you can see the physical properties. Okay, it looks I'm telling you, it looks simple, but it is not actually. When you do the actual calculation, collection of physical property is not that much easy. Okay, so you need to understand the procedure very carefully. Okay, if you have doubt, please discuss. Okay, so and I will tell you, like when you will solve a problem on your own, then you will have better understanding of this. Okay, just 1 minute, beta, huh? Just please, 1 minute. Hello, 119. अच्छा, 119 ठीक है। अभी वो दिया है क्या चल रहा है, पर थोड़ी सी शुगर डाल देना ग्राम हाफ स्पून। ठीक ठीक, थैंक यू। So I'm sorry for the interruption. So in that way you can collect the uh, physical properties of the fluid. I hope you have understood the procedure for that. Now once I'm having the specific heat, we can find out heat duty. So I'm having Q value. So next is to find out the heat transfer area. Okay, so to find out heat transfer area, equation is Q is equal to UA delta T mean. So we need to find out U, we need to find out delta T mean. Okay, so next step is to find out U value, and as U value depend on many other parameters, so so initially we will assume some value of U naught, which we have denoted with U naught assumed, ASS, right? And that we have already discussed before, that we will use this graph available in volume 6. So that I have already explained that if you need any fluid that you can trace, let's say you are having paraffin or something, so middle of that you need to locate, and then middle of the surface fluid you need to locate, or another fluid, second fluid you need to locate. You need to draw these, draw the line for what we can say, joining these 2 points, and wherever it will cut this line there, that value you will consider as overall heat transfer coefficient assumed, right? So that we can discuss, so that we have already discussed. Okay, so once I'm having u assumed, we need to find out delta T mean, because all terminal temperatures of both the fluids you have already calculated. So we need to find out delta T mean, and that delta T mean should be true delta T mean. And for that, initially we assume that one shell two tube passes. Okay, 1 2 shell and tube heat exchanger. Okay, that is the initial guess. And for this you need ft chart, ft value from chart 1 2 shell in tube, 2 4 shell in tube. For that ft chart are different. Okay, so you need to consider the correct ft chart, and based on terminal temperature you can find r and p value. You can see the ft value, and then that ft value you can consider to find out true LMTD. Okay, or LMTD, whatever you need to calculate, that should be for counter current. Please consider this should not be for co-current. Okay, counter current, and then ft factor will be multiplied to get true LMTD. Okay, so in that way you can find out the delta T mean. You have already you are already having u value, so you can find out heat transfer area. Okay, so this heat transfer area will be the heat transfer area of the exchanger. Okay, now once I'm having the heat transfer area, we can then decide this type of what? Type of heat exchanger, like which heat exchanger. That should be fixed tube, U tube, internal floating, external floating, whatever, depending upon different condition, and that I have already discussed in the previous classes. Okay, so which exchanger, that we can see. And tube size means length and diameter of the tube, or how to see that also we have discussed. I will provide the standard chart, standard table for that. Tube arrangement, that should be triangular pitch, square pitch, whatever. Start with triangular pitch, that is in most of the cases that will work. Okay, so start with the triangular pitch. Please keep on please consider these points while designing. Okay, I don't know whether you people are preparing notes or not. Okay, just because everything I cannot include in PPTs. Okay, so you can see you can note down these small points. Okay, but I believe that you are already having the recording, so you can listen that repeatedly. Tube arrangement, triangular pitch, you need to start with. Fluid allocation, very important, that we have discussed I think 1 or 2 class back. Their fluid allocation to tube side and shell side, that, and order, priority order also we have discussed. Okay, so based on that you will assign the fluid to shell side or tube side. Okay, now once you have all these parameters you can fix, then you can calculate number of tubes. Simple. Total heat transfer area you have calculate, you have tube dimension. So area of one tube you can find out, and then you can calculate the heat transfer area. Just keep one thing in mind, as you are considering U not over here. Okay, UO, assume you have calculate, it means overall heat transfer coefficient based on outer surface. I hope you understand the difference between UO and UI, right? So UO will be overall heat transfer coefficient based on outer surface. So this area, whatever you have found, you have calculated, that is based on outer tube surface. Okay, therefore whatever area of single tube you will consider, that should be pi d naught L, right? D naught you should consider there, not di. I hope you are getting my point. Okay, so if you are considering this as ui, this would be ai, and here you need to consider di. Okay, another point to keep in mind over here, that the length whatever you are considering for the tube, that is the whole tube length. Okay, and from two sides it will be from two side, certain part of the tube sheet will, certain part of the tube length will be inserted in tube sheet. Okay, certain part of the tube length will be inserted in tube sheet at both the side. Okay, so whatever would be the tube sheet thickness from at two side, that you need to deduct from the total length. Okay, because whatever length is inside the tube sheet, it will not participate in heat transfer. I hope you are getting my point. So the tube sheet, area of one tube you need to calculate as pi d naught L effective. Okay, L effective would be total length of the tube minus twice of tube sheet thickness, right? So that you need to consider to calculate area of one tube, then number of tube you can find out. That is simple calculation. The number of tubes, we can proceed for shell dia, and for that shell dia you need to calculate bundle dia first. Okay, bundle dia would be number of tubes and this K1 and N1, D naught. Here also you need to consider D naught. K1 and N1 will depend on the passes, and these passes will be tube passes, not the shell passes, and that depends on the pitch. So if you consider triangular pitch, depending upon the number of passes, let's say number of passes are 1 2 heat exchanger, so that should be 2, right? That should be 2. So K1 N1 you can figure out from here, and then you can calculate bundle diameter, right? And once I'm having this bundle dia, you can calculate shell dia by adding clearance into bundle dia, and that clearance will depend on the type of heat exchanger you are considering. Okay, so that you have already decided before, and based on that you can see clearance, and that clearance will be at both the side. Okay, if you see, this is a shell inside dia minus bundle dia, it means that if you consider the heat exchanger uh, like from upper gap as well as below gap, everywhere this clearance has counted. Okay, so you don't need to twice this clearance and then add. Simple, you need to add the clearance which is already mentioned over here. Okay, so in that way you can find out shell diameter. Okay, now once I'm having this shell diameter, we can calculate the tube side heat transfer coefficient. Okay, and that tube side heat transfer coefficient, I don't know whether it will reach to the hyperlink. I don't think it is it has reached to the right slide. What you are seeing right now, the same flow chart, I guess. Yes. Hello.
Yes,
Yes,
ma'am,
ma'am.
the same flowchart. It has not
Same
changed.
flow chart. Okay, okay. So I think this hyperlink is not working. Okay, I'm just sharing that right PPT. Okay. So I hope it is visible clearly now. We are with tube side heat transfer coefficient slide. Yes?
Yes, ma'am.
Okay, okay. Thank you. So just a moment, I'll start. Okay, so when we consider this tube side heat transfer coefficient, as you can see over here, uh, this tube side heat transfer coefficient, if you consider this geometry, or we can say this image, the tube is nothing but the straight pipe. Okay, so we will calculate the heat transfer coefficient uh, which we usually consider in double pipe heat exchanger for inner surface and all. Okay, or flow in a pipe we can say, consider over here. Okay, because this is the straight pipe only, straight tube only. So here simple these heat transfer coefficient correlations you have already read in heat transfer course, and here we have different condition, like if turbulent flow is there, laminar flow is there, transition flow is there. So in that case because for I will tell you that how to uh, further calculate the tube side calculations. Like if you will start computing this tube side heat transfer coefficient, first of all you need to find out the velocity, because you need to calculate Reynolds number. Prandtl number for this properties are already with you. Okay, so Reynolds number, for that you need to find out that what I can say, the velocity. Okay, and that velocity will depend on the type, depend on the number of tubes, depend on the type, depend on the passes. Okay, so let's say if you are considering 1-2 pass, okay, it means the fluid initially uh, will be inserted or will be passed through only half of the tubes. Okay, because of the because of the 2 pass, uh, uh, only fluid will be allocated to half of the tubes, half number of the tubes. Okay, and then it will complete the whole length of the tube, reverse back, and then it will enter to another half of the tubes. I hope you are getting my point. So once it is entering to the tubes, we can calculate the velocity, because you are already aware of the cross section area, density and all. So you can find out the from the flow rate to velocity. Once I'm having the velocity, you can find out Reynolds number. You can locate that in which region we are. Okay, that should be in turbulent or laminar or what, and whatever range of range of Reynolds number will be applicable. It is simply related to the straight pipe, like 2100, less than that laminar flow, and 4000 and above turbulent flow, and in between transition flow. Okay, so you can simply see this, simply use these equations. Okay, and transition flow, when I am considering, you need to calculate from both of the equations, and you need to choose the lesser value. Okay, so in that way you can find out the heat transfer coefficient. However, if you are dealing with the water, okay, if you are dealing with the water, uh, I don't say that these equations would give the wrong value. No, but more accurate value you will get from here. Okay, so if you are using water in tube side, okay, not in shell side, this is for HI only. Okay, So if you are having water in tube side, you can use this equation. Okay, it is given in volume 6 that like T, if you are considering this is average temperature of the water, UT is the velocity of the water, and this DI is the diameter, inner diameter of the tube. Okay, so in that way you can find out inside heat transfer coefficient or tube side heat transfer coefficient more precisely for water. Okay, so one thing is you already are given different correlations, as you can see over here. More precisely for water we are using this, and there is another way, like if you don't know that or you don't want to locate that in which region the fluid is falling, okay, either laminar or turbulent, whatever, you can use this equation which is quite uniform for all regions. Okay, so you can consider this, and once I'm having this, you need to find out this JH, and this JH is the heat transfer factor. Okay, this that JH you can find from here. This graph is given in volume 6. All these graph table, everything will be given to you, and you need to simply understand the procedure and follow it. So if you can see for this laminar zone 2000 and less than, it depends on the L by D. If you can see over here, this is DE by L. So this is this factor is already with laminar flow, which is already considered in this graph. Okay, so you can see depending upon this Reynolds number, you can find out this JH value. Once I'm having this JH value, you can use this graph. Okay, so this is the Nusselt number, so you can directly calculate HI from here. Now if you are given water, okay, you can use this equation, you can use these equation also, but this equation is specifically designed for water, so it is recommended to use this. Otherwise it's not like your design will be wrong or something, but you will get more accurate design when you will use this correlation for water. Okay, otherwise for other fluids you can use the these equations, okay, with JH. Okay, so in that way you can find out tube side heat transfer coefficient. Now steps to calculate heat transfer coefficient, like something I have already discussed with you about this. So based on tube passes, okay, based on tube passes, the number of tubes per pass will be calculated. Okay, if you let's say you are having total 100 tubes, so 50 will be in one pass. Okay, so number of tube per pass you can calculate. You are already aware of DI, so cross section area of one tube you can calculate, and cross section area of all tube in one pass, like 50 tubes cross sectional area you can calculate, right? So once I'm having this calculation for tube per pass, you can find out the fluid velocity. Okay, because you are given mass flow rate, you are aware of density, you are aware of cross flow, cross sectional flow, so you can calculate fluid velocity of the tube. Okay, and check it. How you need to check it? This should be, if it is process fluid, this should be 1 to 2 meter per second. And if it is water, it should be 1.5 to 2.5 meter per second. Okay, if you get the value within this range, it is fine. Otherwise, if you are having lesser velocity, you need to increase the passes. Okay, so let's say if I'm having 1-2 pass, now I am having 1-4 pass. You are not changing shell pass, only consider tube pass. Okay, shell pass आप कब change करेंगे? शेल पास आप चेंज करेंगे जब आपकी जो आपने LMTD कैलकुलेट किया था, in that case FT value, if you are finding less than 0.75, then only you will change shell passes. Okay, however if you are considering tube side pass, you need to change. No need to change shell pass. 1, 2, 1, 4, 1, 8, 1, 16, all these passes are available. Okay, and for that ft value will not change. Ft value will change only with the change in shell passes. I hope you are getting my point. Okay, so if you are considering, let's say 1, 2 pass will not work, you will increase the you will increase it to 1, 4 pass. And when you are considering 1, 4 pass, uh, let's say 100 tubes you are dealing with, so now per pass you will have only 25 tubes. Okay, so those 25 whatever mass flow rate will be available, it will be allocated to, it will be assigned to 25 passes only. So whatever velocity you will consider, more velocity you can expect. Okay, so in that way you can argue that we can have simply double velocity. Let's say if velocity is coming let's say 0.8, so if you increase the pass by 2, velocity should be 1.6. Okay, your argument is correct, but the point is number of tube, if you are considering, it should be complete number. Let's say uh, mm, how should I tell that to you? If you, let's say you are having 90 tubes, okay, so 90 tubes, just if you are making half of that 90 tubes, so 45 tubes will be there. Okay, 45 tubes will be there. Now if you are making that 1/4, it should be 22.5. Okay, but in that case you need to consider number of tubes as complete number, so that should be 23. Okay, so 23, if you are considering, velocity will change, not velocity will not be double, just slight variation you can observe in velocity. So in that case all these points you need to consider. Okay, so you need to bring the velocity into this range. After that you need to consider appropriate heat transfer coefficient correlation and find out the heat transfer coefficient for tube side. Okay, I hope you are getting my point. So that is about the tube side. Let's go back to the chart, flow chart. So tube side coefficient we have already discussed. Once I am having tube side coefficient, that is HI, okay, you need to proceed for shell side calculation. Shell side calculation means you need to calculate the shell side heat transfer coefficient, and for that you need to decide the baffle spacing and baffle cut. Okay, how to decide that? That we have discussed in the last class. Okay, and then you will proceed for shell side heat transfer coefficient. Okay, so let's see that further. So I hope you are able to see the slide with shell side heat transfer coefficient, and in this uh, this is the shell side, and if you consider the shell side, okay, the geometry in shell side is much more complicated than tube side. Tube side is only the straight tube, nothing else. Okay, but if you consider shell side, I'm having complete bundle of the tubes through which fluid will flow. Okay, I'm having baffles, I'm having tie rod, support rod, everything is there. Okay, so the geometry of shell side is much more complicated, and therefore we should understand the flow pattern in shell side. Okay, flow pattern in shells of segmentally baffled heat exchanger. Segmentally baffled means we have discussed the baffles, and if I'm having a baffle cut from one side, okay, from or what I can say, horizontal. If I'm having the baffle, if you visualize the baffle, that is nothing but the disc, okay, in which holes are there, which is aligned with the holes in the tube sheet, right? So this is nothing but the plate, and you cut horizontal part at the bottom or at the top of the baffle, that we call as segmentally baffled heat exchanger. Okay, so the flow pattern is complex in that, and this makes the prediction of shell side heat transfer coefficient and pressure drop much more difficult in comparison to tube side. Okay, so let's see that now I'm having different methods to design shell and tube heat exchanger. Okay, and different methods will what we can say will differ in accordance with the shell side calculation only. Tube side calculation will be same in all, because that is what we can say quite e I think quite easy, or we can say already understood, because that is the flow in a straight pipeline. Okay, so for that whatever standard methods are available, that standard method is available that we can use, but there are different methods for shell side calculations. Okay, shell side heat transfer coefficient and pressure drop calculations, and uh, one method, the first method, or we can say the first method, uh, which is uh, uh, which is, or we can say um, the very first or most like very early it is, this method is given, and that we call as the Kern's method. Okay, you must have heard about the heat transfer book by Kern. Okay, so that Kern's method is given for shell side heat transfer coefficient, and this method is based on experimental work on commercial exchangers, and it gives reasonably satisfactory prediction of what we can say the heat transfer coefficient and pressure drop. Okay, so heat transfer coefficient for standard designs, and for this certain steps we need to follow. First of all, to understand the cross flow area. Okay, for tube side calculation already methods are already correlations are available. You need to only utilize that, but here you need to understand the steps also, the procedure also, or we can say the correlation also. Initially we will discuss about the cross flow area. Okay, now if you consider this particular schematic, this is what we can say the um, front view of uh, heat exchanger. Okay, here I am having the tubes. Okay, and these are the baffles. These are the baffles. These are segmentally baffled because one section is cut. It is cut from here. It has the cut from here like that. Okay, so what we can say that here I am having the baffles. Fine, and this is the shell. Okay, this is the shell. Okay, these are the tubes. So if you can visualize over here, I'm having the uh, gap between baffle hole and tube OD, so that baffle can be inserted smoothly in this bundle. Okay, now if I consider this cross flow, there are different streams which are given standard names like A, B, and E. These three are shown over here. Other streams are also there that we will discuss when time comes. But here for cross flow, we will consider only this B. Okay, if you consider the flow over here, if you consider this part, okay, in that case fluid flow will be parallel to the flow in the tube, either co-current or counter current, doesn't matter, okay, but that would be parallel. If I consider that part which is in between baffle tips, one tip is this, another tip is this, so between baffle tips, if I am considering the flow, that will be cross flow in terms of shell side flow and the fluid which is moving in tube side, so that will be considered as cross flow. So cross flow zone will be available between two baffle tips. Okay, so I hope you understand the cross flow. Now in Kern's method, what we have considered that cross flow area, okay, cross flow, you understand? This area is based upon maximum flow area at nearest tube row to the central line of the shell. Please try and understand, this is not what we can say easy. Cross flow area, it is easy to predict, no problem, okay, but in the cross flow area you need to consider maximum flow area, okay, and maximum flow area, where you will find it, that will be at the center, okay, because let me discuss that. Okay, if I consider the cross section, okay, please bear with me, I'm not getting a perfect circle, right? So this is the cross section, okay, central line means this line at the center. So the as I'm moving from center to above or below, the tubes will be, or number of tubes will keep on reducing. Okay, if I considering the tube bundle, the maximum tubes are available at center instead of this line, instead of this line. I hope you are getting me. I'm trying to just this is the central line, so whatever number of tubes will be available, that would be maximum over here. Okay, so maximum flow area at nearest tube row to the central line. Okay, so maximum flow area means, because here I'm having the maximum tube, so maximum gap between the tubes will also be available here. Okay, like if I consider tubes, if I consider this line, so number of tubes will be lesser in this line in comparison to central line. Okay, I hope I'm able to convey this fact. So at the center I'm having maximum number of tubes. Okay, if maximum number of tubes are available, the flow area will be available maximum. Okay, so the length of the flow area is the baffle spacing. Okay, now if I'm considering the flow area, length of the flow area between two baffle tips, that is nothing but the baffle spacing. Fine, between here, from here to here only, like this. Okay, consider this as a straight line. Okay, so if this is the baffle spacing and that is the length of the flow area. Okay, the what we can say, the uh, another dimension of the flow area would be the space between tubes at the central line. Okay, and how you can find out, that is the cross flow area, it is denoted by AS, that is PT minus D naught by PT. PT is the pitch minus D naught, okay, because PT is the center to center distance between two consecutive tubes, right? So if I'm considering D, if I'm deducting D naught, it will give me the flow, uh, or we can say the gap between the between two tubes. Okay, divide by PT, it means this is the what we can say, the the factor which denotes the flow, what we can say, flow percentage, you can understand, percentage or flow fraction, okay, between two consecutive tubes. And if I multiply that by ds is the shell dia, okay, shell inner dia from here to here, okay, because I'm considering central line, so that should be ds would be the shell dia into this factor will give the total flow area in shell side at the central line. I hope you are getting. Into LB. LB is the baffle spacing, that will be this. Okay. So if you consider this AS, that is the cross flow area at the center, or we can say the maximum cross flow area, right? So in that way you can find out this AS, and depending upon that AS you can find out shell velocity, like mass velocity you can find out by mass flow rate by AS, or simply you can calculate US, that is the shell velocity at the center. Okay, now I'm this velocity, I need to find out the equivalent diameter, because geometry is so complicated, you cannot consider DO or DI. I need to find equivalent diameter. So for square pitch, equivalent diameter you can calculate from this expression. For triangular pitch, you can use this expression. Okay. Once I'm having this, we can find out shell side Reynolds number, and that would be this one. In that case, you need to consider DE. Okay, not DO, because that is the in shell side you will have the uh, hazy flow, very hazy flow. Okay, so with, that we can count with equivalent diameter. Okay, once I'm having this shell, once I'm having this Reynolds number, we can find out shell side heat transfer coefficient considering this graph. Okay, where this heat transfer factor is, you can see from here. So here you need to consider baffle cut. Okay. So baffle cut will be, if you remember the last class we have discussed, baffle cut varies from 15 to 45 percentage. Okay, but that percentage, any value in between two, you cannot say, you cannot take. If it will not work for 15, you need to consider 25, not 20. Okay. In that way, if you remember the last class, there I have discussed baffle cut as the optimum value is 20 to 25, but you need to consider 25 only, not 20, right? So in that way, we can proceed for, we can calculate shell side heat transfer coefficient. Okay, flow chart. Just let me share the screen. Okay. So we have already seen the shell side heat transfer coefficient. Once I'm having this, we can calculate overall heat transfer coefficient, because you have a HI, that is in tube side coefficient, HO shell side heat transfer coefficient, dirt factors. You will already consider that while assigning the fluid from the standard table. Okay, so and thermal conductivity of the material that you need to see. Okay, so now I am having all values to calculate overall heat transfer coefficient from this, and then I need to compare this overall heat transfer coefficient with the assumed value, and that should be within plus minus 30%. If it is not, you need to replace assumed value with the calculated value, and then repeat the whole calculation. Okay. Now if this value of coefficient falling fall within plus minus 30%, you can estimate tube side and shell side pressure drop. Uh, uh, Again, I need to share the screen for pressure drop. So in that, once I'm having heat transfer coefficient, we can proceed for sorry, pressure drop calculation for tube side as well as for shell side. So tube side, when we consider tube side, this is the empirical correlation where I'm having NP is the number of passes which you can fix with the velocity of tube side. JF is the friction factor coefficient that we will see from the graph. From this, okay, L the tube length and this DI tube inner dia, and this is the viscosity correction factor. And here if you see, I'm having 2.5. This one factor is basically used to counter the friction. Okay, now if I consider 1-2 pass, right, if I'm considering 1-2 pass, what will happen in 1-2 pass? Tube half number of the tubes fluid will enter once. Okay, so when the fluid will enter from tube side to the number of two different tubes, there we will have contraction in the fluid. Fine. So I hope you have performed the experiment in fluid dynamics lab, that fluid through elbow, fluid through different diameter, from larger diameter to smaller diameter, that would be contraction. From smaller diameter to larger diameter, that would be expansion. Okay, from elbow, from different walls and all. So that pressure drop calculation experiment you must have done. So if you consider this, I'm having in 1-2 pass. Okay, in 1-2 pass I'm having 2 contraction. Okay, because fluid will enter twice in the tube sheets. Okay, sorry, not tube sheet, twice in the tubes. Okay, so 2 contraction will be there and twice it will exit the tubes. So 2 expansion will be there. Okay, and in 1-2 pass, from what we can say feed end, fluid will enter in the tube, and that rear end or the back end, it will reverse and then re-enter into the tubes. Okay, so it means there I am having 180-degree bend. Okay, so it will also create the friction. Okay, so if I consider the contraction, there I am having friction loss factor as we can say the head loss as 0.5, expansion it has head loss as 1, and 180 it has what we can say the head loss as 1.5. Okay, so 2 contraction, it means 0.5 into 2, 1 value. Expansion may 1, I am considering the loss, so 2 will come from there, and bend is 1 only, so 1.5. So if you add this 2, then 1 plus 2 plus 1.5. Okay, so that would be 4.5 velocity head. Okay, because of the friction loss. Okay, so that would be for 1-2 pass. If I ask you for 1 pass, that should be 4.5 by 2, so 2.25, right? So 2.25, but for what we can say, again to consider some of the minor losses, we consider 2.5 as the head loss, or we can say 2.5 as the friction loss in 1 pass only. That's why it is multiplied by number of passes. Okay, so 2.5 comes from there. Ut is the tube side velocity, which you have already calculated. So based on that, you can find out shell side heat transfer pressure, sorry, tube side heat transfer pressure drop. Okay. Further, for shell side pressure drop, we have this expression, that is JF is the friction factor for shell side. You can calculate, you can see from here depending upon the baffle cut, and that D is shell dia by DE equivalent dia, L is the total length, and LB is the baffle spacing, US is the shell velocity. You have already calculated. So based on that, we can find out this uh, what we can say shell side pressure drop. Okay, here we have this LB. LB is the what we can say baffle spacing, and baffle spacing you can find out by uh, number of baffles plus 1. Okay, because at one end it will be like um, it will start from the tube sheet. Okay, so baffles are in between, so whatever number of baffles you have, plus 1 would be the that what we can say baffle spacing. Okay, so that would be the uh, L by LB you can find out by this NB plus 1. Okay, so in that way you can find out shell side pressure drop. Okay. Okay, so once you have this shell side and tube side pressure drops, you can see the permissible limit of that we have already discussed, and if it is specified by the designer that this much pressure drop should be we need to maintain that, then this value you need to consider. And just a moment. Hello. So here you see if pressure drop is within the permissible limit, we can accept the design. Otherwise, we need to make some changes and then start from here. Okay. So if pressure drop, like if pressure drop is more for shell side, you need to you can increase the baffle cut or baffle spacing. Okay, only this much you need to recheck. However, if you consider for tube side pressure drop is more, then for instead of triangular pitch you can proceed for square pitch, and also from here all calculation will be changed, so that you need to keep in mind. Okay, so just try to bring the values within the permissible limit with the least variation. Okay, and that you need to consider by what we can say in when you will that you need to be intuitive while designing. Okay, so that is about the design procedure. I have already explained each and every term in this very in detail, and that will be more clear when you will solve a problem. And we will consider some of the things that what should be done. What should be done? That need to increase heat transfer. Okay, if I need to increase the heat transfer coefficient, or if I need to increase the surface area. Okay, mostly we deal with heat transfer coefficient to bring that into permissible limit. So if you need to increase the heat transfer coefficient for tube side, you can increase passes. Okay, tube side pressure tube side coefficient will increase because it will increase the velocity, and then Reynolds number will be increased, and so the heat transfer coefficient. But at the same time it will increase pressure drop also, so that you need to keep in mind. Okay, so shell side, if I am considering, we need to decrease the shell, decrease the baffle spacing and baffle cut. Okay, to increase the area, we need to increase the tube length, we need to increase diameter and appropriate number of tubes, and then we need to consider multiple multiple shells in series. Okay, that you need to consider. Okay, to bring the pressure drop to the permissible limit. If you need to reduce the pressure drop, what you need to do in tube side, you need to decrease the passes. Okay, if you need to increase the heat transfer coefficient, you need to increase the passes, but as I told you, it will increase pressure drop also. So this pressure drop will be like increasing. You need to reduce this, and you need to bring the pressure you need to bring the heat transfer coefficient by some other changes. Okay, like tube diameter and all that you can change. Okay, increase the tube diameter. For that, pressure drop will increase, will reduce, but it will uh, it, it will reduce pressure drop also, but not as, what we can say, not very large gap, large value. Okay, decrease tube length and increase the tubes. Okay, in that way you can reduce the pressure drop. Shell side, if you need to reduce the pressure drop, we need to increase the baffle cut, baffle spacing also you need to increase, and then you need to increase the tube pitch from square to, from triangular to square. Okay, in that way you can do some changes. You should be more intuitive while designing the shell and tube heat exchanger, and therefore we say that one solution in the design is not expected. You may have different design depending upon your uh, uh, what we can say, limits. Okay, so depending upon the intuition as well. Okay, so in that way you need to proceed towards the feasible design by changing certain parameters. Okay, so yeah, so that's all from my side for today. We will we will discuss a problem in detail from next slide. Okay, from next class. Sorry, from next class. Okay, so please assemble for next class, and that may happen tomorrow. So that's all from my side for today. So thank you everyone for your patience. If you have any query, we can discuss. So anything you need to make, any observation? Hello? Anyone is there? Okay. So I hope if nothing is there, so I should leave. You please go through this, and then we will solve the problem in next class. So thank you everyone for your patience.